Greetings of the day. I am Dr. Ronika Parmar and I welcome you all to today's course on Fundamental of Electronic Engineering. We are going to discuss about JFET output and transfer characteristics. In today's discussion, we will delve into the fascinating world of junction field effect transistor characteristics. So, in today's lecture, we are going to discuss JFET characteristics, output characteristics of a n-channel JFET, relation between VGS and VP, transfer characteristics of n-channel JFET, JFET parameters. In the JFET parameters, we will discuss about drain resistance known as RD, transconductance and amplification factor. So, let us discuss about JFET characteristics. JFET, it stands for junction field effect transistor. JFET characteristics refers to unique property and behavior exhibited by JFETs, which are semiconductor devices used in electronic circuits. These characteristics are essential for understanding how JFETs operate and how they can be efficiently used in various applications. To understand electrical behavior of a junction field effect transistor, it is necessary to study the interrelation between the current and the voltage in a JFET. These relationships can be plotted graphically, which are commonly known as characteristics of junction field effect transistor. Here are the key characteristics of the JFETs. JFETs are voltage control devices. This means their operation is primarily dependent by the voltage applied at their gate terminal, as JFET is affected by the electric field. So, their operations highly depend upon the voltage applied at the gate terminal. This terminal, the voltage applied at this terminal is known as gate voltage and it is represented as VGS. It is gate to source voltage. Next important thing is high input impedance. One of the most notable characteristics of a JFET is they are exceptionally high input impedance. This property allows them to interface with high input impedance sources without loading the source signal significantly. The voltage controlled device provides a good control over the current. So, voltage operated current control JFETs, they control the current flowing between their source and drain terminal. The drain terminal current is known as ID or the drain current. This is affected by the voltage applied at the gate terminal. As I have told you, gate terminal voltage is written as VGS. So, by verifying the VGS, you can control the drain current. That is, by varying the gate voltage, you can vary the drain current. So, VGS controls ID. An increase in negative VGS allow the channel reducing ID, that is drain current, while a decrease in negative VGS widens the channel, increasing ID. Next important term in JFET characteristics is the pinch off voltage. The pinch off voltage is represented as Vp. Pinch off voltage is a critical parameter in JFET characteristics. It's the voltage at which the channel between the source and drain closes or pinches off. Beyond the pinch off voltage, ID remains relatively constant, making the JFET behave like a voltage controlled current source. So, this is the important term, that the JFET behaves like a voltage controlled current source. The next important term is output characteristics. The output characteristics of a JFET shows the relationship between voltage between the drain source terminal VDS and the drain current represented as ID for various values of VGS. As VGS becomes more negative, ID increases and the curve shifts downward. So, whenever we talk about output characteristics, see the term output shows we have to work on the output side of the device. So, if we say the term characteristics, output characteristics, in the y axis there will be drain current and in the x axis there will be drain voltage. It will be the same in all the cases. So, whenever anyone says about the output characteristics, always remember the drain current will be at the y axis and the drain voltage will be at the x axis. So, here the drain voltage will be VDS, it will be represented as VDS, drain to source voltage, and the y axis will represent drain current, which is represented as ID, and the value of the gate voltage is constant. So, we will keep the gate voltage constant and we will vary the value for VD and ID. Next is transfer characteristics. Transfer characteristics represents the relation between VGS and ID for a constant value of VDS. So, this is the relationship between the gate voltage and the drain current. As I have told you, drain current will always be on the y axis, and here we are deriving the transfer characteristics. So, the gate voltage will be at the x axis, and here we will draw the characteristics keeping the drain voltage constant. As VGS becomes more negative, ID decreases. So, as the gate voltage becomes more negative, drain current decreases, showing that the voltage controlled behavior of a junction field effect transistor. So, there are various regions in the characteristics, and those are cutoff region, triode region and saturation region. JFET operation can be categorized into cutoff, triode is also known as ohmic region, and saturation region. In the cutoff region, drain current is very low. In the triode region, drain current varies with drain voltage and the gate source voltage. In the saturation region, drain currents remain relatively constant. So, basically the characteristics are divided into three categories. First is the cutoff region, second is the triode region, and third is the saturation region. So, in the cutoff region, the value of the drain current, which is ID, current flowing is very low in amount. In the triode region, drain current increases with respect to the increase in the drain voltage. As we will increase the drain voltage, the drain current will also increase. when the drain voltage reaches to the saturation value, the drain current turns out to be constant. So, a constant current flows in the saturation region. It is not necessarily very constant, it will be relatively constant. The important characteristics of JFET are the drain characteristics and the transfer characteristics. The following section explains these characteristics in detail. So, figure 1 shows the drain characteristics of a n-channel JFET. The curve represents the relationship between the drain current and the drain voltage for different value of gate voltage. So, here in this curve we can see the output characteristics. Output characteristics are also known as drain characteristics. So, in this curve we can see the output characteristics of a JFET. These are the characteristics for a n-channel JFET. So, here we can find, as I have told you, in all the characteristics ID will be at the y axis. So, this is our output current and we are discussing the output characteristics. So, our output current will be at the y axis and our output voltage will be at the x axis. So, the y axis contains ID and our x axis contains VDS, that is drain voltage. So, and I have told you the characteristics are divided into 3 sections. First is the cutoff region, then is the ohmic region, followed by the saturation region. So, when we apply the drain voltage and we keep the gate voltage constant, at the starting case when the VDS is very low, almost no current flows in the circuit. The drain current is very less. So, when the VDS increases, the curve goes into the ohmic region and the current increases with the applied voltage. Now, this increase continues and a pinch of voltage is reached. This is known as the knee voltage. So, here we can see Vp mentioned in the curve. So, this is also known as the knee voltage, and post to the pinch of voltage the current goes in a straight line. So, this shows the current is saturated and almost a constant current is flowing in the circuit after the drain voltage reaches to the saturation value. So, we can see this curve there are various curves in this single figure. So, these are for the value of different values of VGS. So, first we can see it is for -4, then it is for -3, then VGS is equals to -2 and then -1. So, whenever we draw the drain characteristics or the output characteristics, our output values will be varying and the input will remain the same. Here input is our gate voltage. So, the gate voltage is kept constant and the VD is varied. Now, as the variation in VD occurs, the output current varies. So, the variation between the drain current with respect to the drain voltage. As we increase the drain voltage, the drain current increases at the starting stage and then it saturates after a certain value. This figure shows the experimental setup required to plot these characteristics. So, as I have told you, the Vg is kept constant. So, a constant VGS is applied to the circuit and then the drain current is measured and the drain voltage is also varied. So, we can see there is a arrow line at the battery side showing there is a variation in VDD. So, here the value of VDS is varied and variation in the drain current is observed. So, from these characteristics we have observed the following points: VGS and VDS, gate source voltage and drain source voltage, both are equals to 0. So, when VGS is equals to 0, the channel is entirely open, but here VDS is 0. So, there is no attractive force for the majority carriers to move, hence there will be no drain current flowing in the circuit. Here our majority carriers are electrons. So, when VDS is 0, no current flows in the circuit. Self pinch off at no bias, that is at VGS equals to 0. So, at VGS equals to 0, in response to a small applied voltage to VDS, that is drain voltage, the N-type bar acts as a simple semiconductor resistor and the current increases linearly with the drain voltage. As VDS increases, the voltage drop along the channel also increases. This increase in voltage drop increases the reverse bias on gate source junction and causes the depletion region to penetrate into the channel, reducing channel width. The effect of reduction in channel width provides more opposition to increase in the drain current, that is ID. Thus, rate of increase in the drain current with respect to the drain voltage is now reduced. This is shown by the curve shape in the characteristics. At some value of VDS, drain current ID cannot be increases further due to reduction in the channel width. Any further increase in the drain voltage does not increase the drain current ID. ID approaches the constant saturation value. The voltage VDS at which the current ID reaches to its constant saturation level is called as pinch off voltage. It is also represented as VP. Gate to source voltage VGS with negative bias. When an external bias, say -1 volt, is applied between the gate and the source, the gate channel junction are further reversed bias, reducing the effective width of the channel available for the conduction. Because of this, drain current will reduce and pinch off voltage is reached at a lower drain current when VGS is equals to 0. This is shown in figure number 1. So, by applying several values of negative external bias voltage at the gate terminal, a family of curves are obtained as shown in figure 1. This can be observed that more negative value of VGS, the pinch off voltage is reached at lesser value of ID. Breakdown region, we can observe from the figure 1 that if we increase value of VDS beyond the pinch off voltage VP, the drain current ID remains constant up to certain value of VDS. If we further exceed VDS, the voltage will be reached at which the gate channel junction breaks down due to avalanche effect. At this point, the drain current increases very rapidly and the device may be destroyed. Ohmic or ohmic and saturation region. It is seen that the drain characteristics of a JFET is divided into two regions, ohmic region and the saturation region. In the ohmic region, the drain current ID varies with VDS, that is the drain voltage, and the JFET is said to behave as voltage variable resistance. In saturation region, the drain current remains fairly constant and does not vary with VDS, that is drain voltage. Saturation in a FET refers to the limiting value to drift velocity. Thus, the number of carriers that can be transported through the channel per unit time is limited or saturated and ID remains constant. It is a very different meaning of saturation than that encountered by the BJT. To use FET as amplifier, it is operated in this saturation region. Cutoff. As we know, for a N-channel JFET, the more negative VGS causes drain current to reduce and pinch off to reach a lower drain current. When VGS is made sufficiently negative, ID is reduced to 0 as shown in this figure, figure number 3. So here we can see the cutoff region in the curve. This is caused by widening of the depletion region to a point where it completely closes the channel. The value of VGS at the cutoff point is designed as VGS is designated as VGS off. So, do not confuse cutoff with pinch off. The pinch off voltage Vp is the value of VDS at which drain current reaches to a constant value for a given value of VGS. It can be observed that the value of VDS for breakdown are reduced as the negative gate is increased or as the negative gate bias is increased. This is because the total reverse breakdown voltage is the addition of the reverse voltage due to self pinch off and the externally applied voltage at the gate terminal. The cutoff voltage VGS off is the value of the gate voltage at which the drain current is 0. So, ID is 0 only when magnitude of VGS is equal or greater than the magnitude of pinch off voltage Vp. So, let us discuss about the relation of VGS off and Vp. ID is 0 when VGS is equals to minus Vp, because a 0 drain current corresponds to an off condition. The magnitude of Vp is equivalent to the magnitude of gate voltage at off condition or VGS off. Most JFET data sheet specify a value only for VGS off and not for Vp. But once we know VGS off, we can also know Vp. For example, if VGS off is equals to minus 4, then Vp is equals to 4 volts. The PN junction between the gate and source is reverse biased and the gate current is practically 0. Then the resistance between the gate and source will be very large. Ideally, it will be infinite. Thus, input impedance of FET is very large. Compared to this, the input impedance of the BJT is small. Also, we have seen that the drain current depends upon the gate voltage and almost independent of VDS. By changing VGS, drain current can be varied. Hence, FET is basically a voltage control device. The input voltage controlling the output current. Figure 4 shows the transfer characteristics of a n-channel JFET. The curve represents the relationship between the drain current and the gate source voltage. This is the transfer characteristics of the n-channel JFET. Here ID is at the y-axis and VGS at the x-axis. From these characteristics, we observed following point. The relationship between the drain current and gate to source voltage is nonlinear. This relationship is defined by this equation ID is equals to IDSS 1 minus VGS upon VP square. The square term for the equation will result in a nonlinear relationship between the drain current and the gate voltage, producing a curve that grows exponentially with decreasing magnitude of VGS. From the equation, we can also write that VGS is equals to VP in bracket 1 minus under root ID upon IDSS. In this equation, the value of IDSS and VP are constant and value of VGS controls the drain current. A point A at the bottom end of the curve on the VGS axis represents VGS off and point B at the top end of the curve on the ID axis represent IDSS. That is, IDSS is maximum drain current at VGS is equals to 0. Thus, this transfer curve shows the operating limits of a junction field effect transistor. So, there are ID is equals to 0 when VGS is equal to VGS off, ID is equals to IDSS when VGS is equals to 0. So, let us discuss about the JFET parameters. First parameter is drain resistance, it is represented as RD. From the drain characteristics, the important parameter of a JFET is drain resistance and it can be calculated using these characteristics. Figure 5 shows the drain characteristics for a n-channel JFET. So, in this curve we can see there is a variation between ID and there is a variation between VDS. So, using this current voltage relationship we can measure the drain resistance. So, this resistance will be measured for a constant value of VGS. The drain resistance RD is the AC resistance between the drain and source terminal when JFET is operating in the saturation region. It is the reciprocal of the slope of the drain characteristics in saturation region. Drain resistance is given by variation in VDS to variation in ID with a constant value of VDS. Next important term is transconductance. Transconductance is the change in the drain current for given change in the gate source voltage with drain to source voltage is constant. It is shown in figure number 6. So, looking at figure 6, we can say that it is the slope of the transfer characteristics. Since the slope varies, GM also varies. Transconductance is represented as GM. So, as the slope varies, GM also varies. GM has a greater value near to the top of the curve than it does near the bottom. So, here we can see the transfer characteristics for a JFET, n-channel JFET, and we can observe GM by variation in ID to the change in gate voltage. The transconductance GM is defined as variation in ID to variation in gate voltage. It is the rate of change of drain current to the change in gate voltage. Transconductance is also known as mutual conductance. The practical unit for GM is millisiemens or milliampere per volts. For a given value of GM, we can calculate an appropriate value of GM at any point on the transfer characteristics using this equation. Next important parameter, so far we have defined two parameters known as GM and RD. For a JFET, the third parameter is known as amplification factor and it is represented as mu. Mu or the amplification factor is the variation in drain to source voltage to the variation in gate to source voltage at a constant value of ID. The amplification factor mu is defined as in term of parameter of GM and RD. Mu is RD into GM. So, this completes the JFET parameters. In this lecture, we have discussed about the JFET characteristics. We have seen the output characteristics and the transfer characteristics. We have seen the relation between the GS and we have seen the relationship between the gate voltage and pinch off voltage. Also, we have discussed about the JFET parameters, that is drain resistance, transconductance and amplification factor. Thank you very much for attending this lecture. Hope to see you soon in the next lecture.